21.3.1 Generation and conduction of nerve impulse. Neurons are excitable cells because their membrane are in a polarized state. Do you know why the membrane of neuron is polarized? Different type of ion channels are present on the neuron membrane. These ion channels are selectively permeable to different ions. When a neuron is not conducting any impulse, that is resting, the axonal membrane is comparatively more permeable to potassium ion and nearly impermeable to sodium ions. Similarly, the membrane is impermeable to negatively charged proteins present in the exoplasm. Consequently, the exoplasm inside the axon contain high concentration of K positive and negatively charged proteins and low concentration of Na positive. In contrast, the fluid outside the axon contains a low concentration of K positive, a higher concentration of Na positive, and thus form a concentration gradient. These ionic gradient across the resting membrane are maintained by a active transport of ions by the sodium-potassium pump, which transport 3Na outwards for 2K into the cell. As a result, the outer surface of the axonal membrane possesses a positive charge while its inner surface becomes negatively charged and therefore is polarized. The electrical potential difference across the resting plasma membrane is called as the resting potential. You might be curious to know about the mechanism of generation of nerve impulse and its conduction along an axon when a stimulus is applied at a site. Figure 2.1.2 example point A. On the polarized membrane, the membrane at the site A becomes freely permeable to Na positive. This leads to a rapid influx of Na positive followed by the reversal of the polarity at that site. That is, the outer surface of the membrane becomes negatively charged and the inner side becomes positively charged. The polarity of the membrane at the site A is thus reversed and hence depolarized. The electrical potential difference across the plasma membrane at the site A is called action potential, which is in fact termed as a nerve impulse. At site immediately ahead the axon, example site B. Membrane has a positive charge on the outer surface and a negative charge on its inner surface. As a result, a current flows on the inner surface from site A to site B. On the outer surface, current flows from site B to site A to complete the circuit of current flow. Hence, the polarity at the site is reversed and an action potential is generated at site B. The sequence is repeated along the length of the axon and consequently the impulse is conducted. The rise in the stimulus-induced permeability to Na positive is extremely short-lived. It is quickly followed by a rise in permeability to K positive. Within a fraction of a second, K positive diffuses outside the membrane and restores the resting potential of the membrane at the site of excitation, and the fiber become once more responsive to further stimulation. 21.3.2 Transmission of impulses. A nerve impulse is transmitted from one neuron to another through junction called synapses. A synapse is formed by the membranes of presynaptic neuron and a postsynaptic neuron, which may or may not be separated by a gap called synaptic cleft. There are two types of synapses, namely electrical synapse and chemical synapse. At electrical synapses, the membranes of pre- and postsynaptic neurons are in very close proximity. Electrical current can flow directly from one neuron into the other across these synapses. Transmission of an impulse across electrical synapses is very similar to the impulse conduction along a single axon. Impulse transmission across an electrical synapse is always faster than across a chemical synapse. Electrical synapses are rare in our system. At a chemical synapse, the membranes of the pre- and postsynaptic neurons are separated by a fluid-filled space called synaptic cleft. Figure 2.1.3. Do you know how the presynaptic neuron transmits an impulse, action potential, across the synaptic cleft to the postsynaptic neuron? Chemicals called neurotransmitters are involved in the transmission of impulses at these synapses. The axon terminals contain vesicles filled with these neurotransmitters. When an impulse action potential arrives at the axon terminal, it stimulates the movement of these synaptic vesicles towards the membrane, where diffuse with the plasma membrane and release their neurotransmitters in the synaptic cleft. The released neurotransmitter bind to their specific receptors present on the postsynaptic membrane. This binding opens ion channel, allowing the entry of ions, which can generate a new potential in the postsynaptic neuron. The new potential developed may be either excitatory or inhibitory.
Goodbye.